Hi kiddos, I'm going to walk you through how to do your work for the trends in spaghetti since I am not going to be here today. First off, some of the things you need. You will need your piece of spaghetti. You will need a ruler. You will need your calculator, highlighter, and you will also need this guy here, the 3D periodic properties data. This is the laminated copy. And these are going to be at the front of the room, right by my gas and air knobs, which are right there. Okay, so before we begin, I just want to make sure that you guys have read through the front here. So here is a blank periodic table, and you can see the categories of the period, and these would be represented by the columns, and you can see the group, which would be represented by the rows. So moving forward, we're going to be using these things synonymously instead of just saying column and row. So for this activity, we are only going to be using the items that are shaded. So only these periods and these rows. That is what we're going to be looking at in order to determine the trends across the periodic table. So knowing that, for number one, here you would fill in the property that I gave you last class. If you were absent, the people around you know which property you were given. You were given either ionization energy, electronegativity, or atomic radius. That should be filled in here. For number two, it says to look down the column for your assigned property and to find the maximum value. The way you would do that is to take a look here. So if we look at our 3D periodic properties data, you can see, sorry, forgive me, I gotta adjust the iPad. You can see that you have each of the different columns represented. You can see the symbol, the atomic number, and then each of the different properties. You are one of these three. And you can see that if we go down the column, you can see each of the different numbers. All you're doing is recording the largest number for each. So for the example, I'm going to be walking you through how to do this with ionization energy. So if we look through each of these numbers, we can find that the max value, and remember that it does go on to the backside, for ionization energy, the max value is right near the top, which is why I chose to do this one as the example. So this number, 2372, the units are kilojoules per mole. You don't know what that is yet, but that's okay. You're just going to record just that. So this is our maximum value, and this would go for number two. But remember that I'm doing the ionization energy. Yours is going to be different. So if you need to push pause to find that, go ahead and push pause. And make sure you're also recording the element. Push pause if you need to. Okay. So the next thing you're doing is measuring your spaghetti. So your length of your spaghetti should be 21 centimeters. We're going to just say that it is anyway. And remember, we want to record with one digit of uncertainty, so it would be 21.0. So we're going to say, and I'm not going to make you measure all of your lengths of spaghetti because that would take forever, and we're not going to do that. But we're going to say that if I gave you a bunch of pieces of spaghetti and you measured all of them, the longest piece is 21 centimeters. So that's what you're going to record there, and you can see I already gave it to you. And then the next thing we're going to be doing, just like we did in the last unit, how we had a scale model, we're going to be making a scaled value here. So if our maximum length of spaghetti is 21.0 centimeters, remember that we're stating that that is the maximum value for our property. So if we have ionization energy, the maximum ionization energy, which we already recorded here, if we were to equate that to spaghetti, the longest spaghetti length would be equal to our maximum ionization energy, or electronegativity, or atomic radius. So I'm going to write that in here. So I had 2372. So that was kilojoules per mole. And remember that if you do not have ionization energy, you should be writing in what your maximum value is for either electronegativity or for atomic radius. So we're stating that this is the max in spaghetti, this is the max for our ionization energy, or whatever your property was. Okay? So now, if we turn the page, now we have a little bit of math. But I don't want you to be scared of the math, because this is just the same stuff we've been doing. It's actually even easier. This is just our multiplication division. You get a calculator the whole time. So now we're taking that ratio that we had for number 3, because back here, this guy, that's a ratio. We're saying that 21 centimeters of spaghetti is equivalent, the maximum length of spaghetti is equivalent to the maximum of your property. So now we're taking that and we're working out how big our spaghetti would be based on whichever element we have, because all we know is that it would be 21 centimeters if it were the maximum, but only one of them is going to be the maximum. So for this sample problem, we're going to use something that is not on the properties table, which is density. So just so you know, we are now looking at density. That is not one of the properties, but this is a sample. So I want you to take a moment, please push pause, and work through this problem independently. What I would like you to do as you're working through this is I want you to identify in each place the mathematical functions that you're doing. And I want you to annotate this sample with how you get to each step. So please press pause and do that. Okay, so now that we're back, remember here that our sample property is density, and our sample element is beryllium, which is one of the elements on the periodic table. So here we're saying that if our maximum density was iron, which is very, very dense, this is the value of iron's density. And remember that we're talking the highest density of any element. And here we're looking at the highest or the longest length of spaghetti. This is our ratio. Longest spaghetti, most dense. That's our ratio right here. Okay, so when we're calculating this with beryllium's density, so just like you're given here, each of the elements' property, here we're pretending that you're given beryllium's property as well. So beryllium has this density. But we know that the greatest density is iron, which is here. So all we're going to do is some cross multiplication to figure out, if we were to make a model using spaghetti, how long our spaghetti length would be. So let's cover this up down here. So we know that our maximum spaghetti length is 21 and our maximum density is here. So if we were looking to be able to figure out how long our spaghetti would be to make one specifically for beryllium, we know that if we have our desired spaghetti length, that's going to be divided by our desired density, or the density that we're given, which is here. So then when we work it out down here, remember what we're solving for is the spaghetti length of the beryllium. So we have to cross multiply. So here, this is, again, the density of our beryllium. Here's our max spaghetti length, max density. So when we cross multiply, we end up with our max spaghetti and our density of our beryllium in the numerator, and our max density in the bottom, which would be our iron. And then it's just multiplication, division, which gives us this value. We're going to round off all the spaghetti lengths to 0.1 centimeter because you are going to be measuring these when you make your model with a ruler, and we really can't estimate that to any smaller. That would be really challenging to physically make your model otherwise. If you need to pause it here and go back, feel free. So now we're moving on to the samples. Again, I'm still working with ionization. So all of you guys will have to do this for the 8 elements given your properties. So here we're looking at using our scale for hydrogen. So remember that we already, back in number 3, said that our maximum spaghetti length was 21 and our maximum ionization length was 2372, and that this was for helium. And if you're having a hard time remembering that, here it is. So here is our ionization energy, and our maximum ionization energy happens to be on the periodic table, atomic number 2. So that's why I chose this one. It's just right there near the top of the table, so you can see exactly where I got that. So we know that these two represent our max. But what we're solving for is how long our spaghetti would be if we were making a model of hydrogen's ionization energy. So we just set it up like this. So here's our desired spaghetti length, and here would be our ionization energy for our hydrogen, which is this value. So 1, 3, 1, 2. And again, I got that right off of the table. And then if we set it up just like we did up here, we can see that we get our maximum spaghetti length times the ionization energy of our hydrogen divided by our maximum ionization energy. Units cancel, units cancel. We're left with only centimeters because what we're looking for is our spaghetti length, and that has to be in centimeters. And one way we can remember how to set this up is if you set it up in a way that your units don't cancel, you've done something wrong, because this tells you what you're looking for, and we know that has to be in centimeters. So this is one example. You guys will be working with your groups to calculate for all of these. Please be mindful of your sig figs, and remember you are rounding to 0.1 centimeters or 1 millimeter. So you're going to be showing the work for your first state elements, finding all of your spaghetti lengths, and then adding those to your table. So this is what you are doing today. You need to make sure that you have this done as precisely as possible so that you are ready to build your model next class. Have a wonderful day.